All right. So we're going to talk today about derivatives of vector valued functions. Next time we'll talk about integrals of vector valued functions. We will, thank you. We will then we'll start applying this derivatives and integrals to some application type problems, talking about projectile motion a little bit. But what we're leading into, kind of the big one of the main ideas with vector valued function, main ideas of chapter 12, is to talk about curvature and arc length, because those are going to be important topics moving forward, and we'll use arc length to help us do a lot of things in chapter 15 when we start doing vector calculus. All right, so our definition of the derivative of a vector valued function. So for a vector valued function r of t, the derivative r prime of t equals, and we're gonna define the derivative of a vector valued function exactly like we define the derivative of a scalar function. It's going to be the limit as delta t approaches 0 of r of t plus delta t minus r of t, vector valued function r of t, over delta t. If r prime exists, then r is differentiable. So this follows exactly our definition of the derivative of a scalar function. So let's draw a picture of what we're talking about here. And then, because we're talking about vectors, this derivative turns out to be very easy to evaluate. So let's say I have a curve here, like so. And we're going to draw some vectors on. Here is where do I want to put it? I'll put it there. It's easier to draw there. So there is r of t. And then we're going to do a vector r of t after a little bit of time, r of t plus delta t. And then the difference between those is going to be this vector that goes between, like so. So that vector is r of t plus delta t minus r of t. That's a difference. And what we're doing here is taking the limit as delta t approaches 0. So this vector gets closer and closer to r of t, just like we did with the scalar function. And we're going to get, as a result, we're going to get a vector here, r prime of t. Now this is the red line is the curve given by r of t. So this is exactly like we did with a scalar function. Just our curve is in 3 dimensions, and we're dealing with vectors. And we can show using the definition of the derivative, and because R of t, we can express R of t as a sum of components. We have an x component, a y component, and a z component. And one of the properties of limits is the limit of a sum is the sum of the limits. So we just take the limit, this limit for each component. Our components are scalar functions. So what we end up doing is that we can see that if R of t is f of t I hat plus g of t j hat plus h of t k hat. We write our vector as a sum of components. Then r prime of t is just f prime of t I hat plus g prime of t j hat plus h prime of t k hat. We just take the derivative component by component. And this is true as long as f, g, and h are differentiable. R prime of t is tangent. R prime, yes, to R of t at the point t, and points in the direction of increasing parameter. So r prime of t gives us a tangent vector to our curve at a particular point, and it's pointing in the direction that parameter increases. So if we think of r of t as the path that some object is moving along, what would r prime of t be? Change of slope. And if we're thinking of an object moving, what do we call that change of slope with respect to the velocity? R prime, if we think of r of t describing the path of something moving, r prime of t is going to be the velocity, the rate of change of its position with respect to time, the velocity. We could take another derivative and get the acceleration with respect to time, if we think of this as a object moving along and time, our parameter is time. So that analogy is going to be useful when we talk about, we will talk about velocity and acceleration, because what we want to get to eventually is a tangential component of acceleration and a normal component of acceleration. And that's going to have to do with curvature as well. All right, questions? So some properties of the derivative of a vector valued function. They are, for the most part, they mirror the properties of a scalar derivative, but there are some important differences and there are some important additions. All right, so we're saying C is a scalar. F is a real valued function. We're saying all of our functions are differentiable. It's a scalar function. And R and U are differentiable vector valued functions. So our first property, the derivative with respect to our parameter of a scalar times a vector valued function is just the scalar times r prime of t. And I just want to point out, it's usually, often we think of our parameter t, we write t, we think of time. A parameter does not necessarily have to be time. It can be just some arbitrary parameter that we've parameterized our curve with. The derivative of a sum or difference is just the sum or difference of the derivatives. And our product rules, we have 3 of them. If we are taking the derivative of a scalar function times a vector valued function, we can just use our normal product rule. And a lot of times we use these product rules not because this is easier to evaluate than just multiplying the functions out and then taking the derivative. A lot of times we use this to go the other direction. We'll see something like this and we recognize that it's a product rule. So kind of to go to the other direction. The derivative of a dot product. It's another way that we can multiply vectors. Is just like our normal product rule. RT dot. I'm going to drop the t, the functional notation. R dot u prime plus r prime dot u.
So you have to keep the dot.
Yeah, these are dot products now. This is a dot product.
Could you just do the dot product?
So yes, you could do the dot product and then take the derivative, or you can find the derivative this way. And again, the way this, most commonly we use this, to, if we see an expression like this, say, oh, that's a dot product, the derivative of a dot product. And then for a cross product, r cross u is r cross u prime plus r prime cross u. Order matters. Because we know that the cross product changes signs if you change the order. So we have to, if we do the dot product or the cross product in a particular order, we have to keep that order. We also have a chain rule. So if we have the derivative of a vector valued function, r of f of t, composed with a scalar function, it's just our normal chain rule. R prime of f of t times f prime of t. This next one is an important one. This one comes up often when we're coming up with equations that have to do with vector valued functions. If the dot product of a vector valued function with itself is a constant, scalar constant, then r dot r prime equals 0. So what does this tell us about r and r prime? They're orthogonal. So if the dot product of a vector value function with itself is a constant, then r dot r prime is orthogonal. And we see this by finding the derivative of r dot r equals a scalar constant. So you do the derivative, use your product rule, and you come up with this. So this comes up later. It'll come up when we talk about acceleration, velocity and acceleration. Will come up when we talk about curvature. So it's an important property of vector valued functions. And the last one, if r prime of t equals the 0 vector, the curve given by r of t has a cusp at that value of t. And so what this tells us is r of t is smooth where r prime of t is not 0. The 0 vector.
0 vector is the vector where all components are just...
All components are 0. So a smooth curve is going to have r prime of t not equal to 0 anyway. Not equal to 0 vector. All right, so what I want to do is go through an example of calculating a quantity that has to do with vector value functions and derivatives, just so we see the process. The interesting thing is that these kinds of problems you end up doing, basically you do 3 problems in one.
Oh, good.
Because you have 3 components.
So you're saying we don't have that much homework?
You get 3 spicy
Instead, we just make sure that it's 2D and
I mean,
have
it's
big
better than
problems.
blocks.
It's 24 blocks? I did it last night.
And I think I told you all that in one of the courses that I took in my master's degree program, we talked about infinite dimensional vectors, where each component of the vector was an infinite sequence. Yeah, so wrapping your head around doing operations with those vectors was kind of interesting. All right, we want to find, first off, before we do anything, t sub 0, yes.
Oh, I thought it was 2.
Oh, let me make my subscript a little smaller. There. How's that? What kind of curve is this?
It's the helix thing again.
Yeah, this is a helix. We get circular motion. We get it moving along a cylinder. And this is going to give us the motion along the z-axis. All right, so we want to find r prime of t0 over the magnitude of r prime at t0. And if we think of this as a particle moving along that helix, what would this give us? A unit vector in the direction of motion. So this is going to give us a unit tangent vector. So this would be a unit tangent vector. And r double prime of t0 over the magnitude of r double prime of t0. And what would that give us?
A unit vector
Unit
for
acceleration,
acceleration.
tangential acceleration.
Vector.
Yes. I can find that.
I think I got there.
So the you physics people, I don't know if you've gotten here yet, but if you took physics before, what kind of what's an example of something that would move in a helix?
A helix.
Something
A charged particle moving in a magnetic field is going to move
I knew that.
in a helical path.
Helical? Is that what they call it?
also tension in springs does the same thing.
Tension and springs.
Yeah.
All right. R prime. Hello.
Wow, president showed up late. Who'd you bribe to get that fast?
All right, everybody, stop. We have to stop talking about JD now. R prime. What's R prime going to be here?
Pi. Negative pi.
Negative pi sine pi t I hat plus pi cosine pi t j hat plus 2t k hat. At t0. And just think about this. I'm thinking about integrating vector valued functions. We could do an integral of the day where one is an integration by parts, one is a partial fraction, one is a trig sub.
No. Why would we not do that?
All right.
Our final is just that.
At t0, r prime of t0 is sine of negative pi fourths.
Negative pi equals negative 1/2.
Negative pi fourths. Sine is negative. There we go. Negative square root of 2 over 2. So we get pi square root of 2 over 2 I hat plus pi square root of 2 over 2 j hat minus
No, you gotta,
1/2 k hat.
you gotta think about it.
Hold up.
The y component's negative,
It's a thing.
at negative pi fourths. It's down in the fourth quadrant. The magnitude, r prime of t0, is the square root.
Oh, goodness.
So we get a little preview of what homework in vector calculus is like.
Oh, Mr. Beamer.
My favorite class.
It's like such a fact.
That was probably sarcastic.
And this gives us pi squared over 2 plus pi squared over 2 plus 1/4, which is square root of pi squared plus 1/4, which is 1/2. For pi squared plus 1.
Can I just use
Yeah, 89 will do that.
So our r prime of t0 over the magnitude of r prime of t0, the first part of our problem, is 1 over, so we get the 1/2 is going to cancel with these 2's here, and we get 1 over the square root of 4 pi squared plus 1 times pi squared of 2 I hat plus pi squared of 2 j hat minus k hat. The 1/2, these 1/2s cancel when we do the reciprocal of that 1/2. All right, there's our unit. That would be a unit tangent vector. We think of this particle moving along that helix. Isn't that nice? Mm-hmm. And I'll tell you what, why don't we, because I don't think we need to do more derivatives, I'm going to erase this part.
So hang on, if we did have to do that derivative, so when we did it with like parametrics, we have that other special rule about second derivatives. You just take another derivative of each and put it separately.
Here we just take we would just take the derivative of this to get r double prime.
And you don't have to like do it.
You know, there's no, it just, you just do because we're just taking derivatives of scalar functions. All right. Questions? Okay. Yeah, not too bad. Not too bad. Yeah, dude, you're going to be doing a lot of derivatives.
How do you feel about those? There's a lot.
I swear to God, if there's any quotient rule in these homeworks, or insane chain rule,
Imagine having to
That's
do
when
one
you
of
put a
those.
question mark and say you can figure it out.
this is where you just say,
That's where you just say, yeah, no, not doing that.
I thought it was
Do you remember that? Okay, so you did the test that had that one quotient rule that had a one-on-one exchange rule in the quotient rule that took literally like 5 minutes to solve, and I was like, wow, this was my entire test was figuring this garbage out. Now you could have to do that 3 times.
And what we end up doing when we talk about tangential and normal components of acceleration, we end up doing derivatives, first and second derivatives, and dot products and cross products, and various combinations of those things.
But so is there a quotient rule that we need to be familiar with, or is that just like the same?
No.
Avoid quotient rule by just not doing it?
What did you say about your quotient rule, Jack? It's not unruly quotient
I
rule.
do it backwards.
Oh, it's a backwards quotient rule.
But like, I think it's the right way, and I like have it.